Hello everybody. I hope you're doing as well as can be expected. So last time we talked about the general concepts behind lighting design in specifically how they related to the lighting plot and the creation of the lighting plot. Today we're going to talk more about the equipment side of things, and I'm going to try to give you an overview of the system that's typically behind our work. So the lighting plot, which we get, which here's an example here, it incorporates quite a bit of mechanical information having to do with not just where we hang the lights in the sense of the design purpose for the lights, but an awful lot about what one can do in a lighting system is involved in this. Before I go into that, I am going to have to delve into some rather particular background information, notably about the nature of lighting instruments themselves, and then about electricity. Sorry about that, and it might even involve a small amount of arithmetic. So there's two large categories that make up the bulk of lighting instruments. And that is the way it's talked about, by the way. So these pieces of equipment are generally not referred to as lights or lamps. In fact, those terms are used in quite specific ways. So for example, the lamp is what you might think of in a conventional lighting instrument as the light bulb. The thing itself is referred to as an instrument. You might occasionally see pretentious people talking about luminaires, although that phase seems to have gone away largely in North America. So the instrument almost always has a lamp, but that's where things start to diverge. So what we think of as conventional lighting instruments have a lamp inside of them. It's typically a more sophisticated version of a tungsten halogen lamp, what you might find in a classic, say, IKEA desk lamp. And there's some reasons for that, but I don't need to go into that right now. It can do basically one thing. It can turn on, the lamp can get brighter and dimmer, and it can turn off. And it does that by being controlled through a dimmer. More on that later. The other huge category of lighting instruments, which has become increasingly common, and especially increasingly common since we designed and specified the equipment for our building, are broadly referred to as intelligent fixtures. Referred to that way because they do things other than turn on and turn off under control of the lighting console, which is fundamentally a computer. And typically, most of them do not have a dimmer behind them, in the sense that all of those functions, including getting brighter and dimmer, are built right into the instrument themselves, and they are controlled from the computer, the lighting console, but they don't actually require being hooked into a dimmer. They require constant power, and frankly, that's one of the things that would be quite different had we designed this building in 5 or 6 years later, because we would have put a lot more circuitry, a lot more access to regular power, although more on that later, all over the lighting grids. And so we have, in fact, put semi-permanent wiring all over the lighting grids. Okay, so in order to discuss how a regular lighting plot running conventional instruments is working, you need to understand electricity on at least on a basic level. So we have roughly two large categories of electricity that we're dealing with. One, represented here by drawing of a couple of batteries, is direct current. So direct current flows constantly in one direction, and let's not get into the physics of this because it's complex. However, you could say that it flows from the negative pole of the battery to the positive pole of the battery if you're hooked up that way. And if you reverse the wires, then it goes the other direction through the lamp. Okay, but the main point about this is that it's steady and it's flowing in one direction. That is no longer the most common system for electrical distribution. Ironically, it was actually the first system for electrical distribution, and there was if you like, a competition in the United States between direct current systems and alternating current systems, and alternating current is the second one. So whereas if you turn on a system that is running direct current, the current goes up to a certain level, and we'll get to that in a minute, and it flows steadily. If you turn on an alternating current system, it varies consistently through a period of time, and it reverses. So it actually starts flowing in one direction and tapers off and crosses to nothing and reverses and crosses over again and reverses to nothing. In short, this is a function of how that current is generated. And what you're looking at here is a sine wave. It's a function of the fact that generators are rotating pieces of equipment, and over time the electricity is making a perfect sine wave if you could graph the intensity of the electricity and over time. What you're looking at here, in fact, is what you would see in a North American system. Although here, the actual size of the electricity, I'll get to that in a second, is not represented. But you can see that this is North American current because it is happening over 1/60th of a second, because in North American alternating current, it changes 60 times a second. Okay, so the frequency of the alternating current is 60 cycles per second, or 60 hertz. We'll get into that in audio. In other parts of the world, it's 50 cycles per second. So you don't need to understand this accurately, except what you do need to grasp is that the current starts flowing, it increases in going in one direction to a maximum, tapers off, crosses over at zero, goes the other direction to the same intensity, and crosses over again at zero. And it does that in North America every 120th of a second. It's reversed, it's a half cycle. And in other systems, it's 100th of a second. Okay, so what's happening at the same time in this graph here, which is a graph of the voltage versus time, and that is happening over in the same way as I just described, over a 60th of a second. Okay, so obviously we need to define some of these terms. All right, so the common analogy for electrical current, which is exactly that, it's an analogy, but it's a way of understanding it. The analogy that's often used is it's like water flowing through a pipe, okay? And you would have three things. One is, if you're looking at water, for example, you have what's the pressure, what's the motive force, the pressure behind the water. That would be equivalent to, in electricity, a unit called the volt, which is also a measure of electromotive force. Okay, how much water flowing at a given instant is not a measure that is over time. In fact, neither is voltage. That is current, and the electrical equivalent of that is the amp, or ampere for current. And so you've got the pressure behind the current, you've got the amount flowing at a given instant. So when you grasp that very rough basic concept, then we can look at the three measurements that this translates to in electricity. So the voltage measured in volts is the electromotive force, and it is it's, as it says right here, it's the pressure in the garden hose. Okay, the amperage is the amount of flow at a given instant. So the rate of flow is current, and that is measured in amps or amperes. By the way, a lot of these are named after people who developed the concepts. Okay, so the missing concept is the watt, or the, as it says here, the method of measuring the rate of energy transfer. So what do you need to know here? Well, you need to know, for us, that watts equals volts times amps. Voltage is different. A lot of you are probably from parts of the world where the voltage is nominally 220 volts or 230 to 230. All of these are usually ranges. So common North American voltage, we would assume, unless somebody tells us different, is between 120 and 130, 130 plus, it varies, but 120 volts of alternating current, 60 cycle. In much of the rest of the world, it's 220 to 240 in that range, and it's alternating at 50 cycles per second. Why? Okay, well, in simple terms, it's because, practically speaking, for the mechanics and the manufacture of the equipment, what makes a difference is the amount of current flowing. So if you have larger current, more electricity flowing at a given instant, you need bigger wires. You need more more durable plugs and wiring systems, because it's the amount of current flowing that affects how how easily things are going to get in the way, like resistance and so on. For those of you for whom this is not even difficult to comprehend, I'm fully aware that there are other formulas that they involve things like resistance, and they use initials like I, but I am trying to keep this pretty dead simple. Okay. The usual question that a lighting technical person is trying to answer is, how many lighting instruments can I put on a given part of the system? And so therefore, the systems are rated typically in amount of current that they are designed to handle. So in North America, if you see a plug on the wall, you can safely assume that that plug is part of a circuit for which the overall capacity is 15 amperes at 125 volts. If you go up into the lighting grid, you're going to find that your regular kind of plug that you could plug into the wall is not going to go in, because every different rated circuit has different plugs. Sometimes they're different because they are designed to handle different amperages. Sometimes they're different because they're designed to go in and twist to lock. That's typical in our theater. Not because they're handling different amperages, but because that way they won't fall out. But say, even if it's a twist lock, there'll be a twist lock for 15 amps, a twist lock for 20 amps, a twist lock for 30 amps, and so on. And there'll be different twist locks or different kinds of connectors here versus in Europe or in Asia, because those are designed to run at 230 volts, not 125 volts. And I could give you a simple comparison. So for example, if watts equals volts times amps, and you have a 100-watt light bulb running here in Canada, you can expect that the wattage, if it stays consistent, if it's a 100-watt light bulb, it's going to be something like 0.8 of an amp at 120 volts. If you run that same light bulb designed for 230 volt power or 220 volt power, it won't be the same light bulb, but it will be running and drawing half that much, more or less half that much. So 0.4 of an amp, because it's running at 220 volts. So, 4.4 times 220 is the same as 0.8 times 120-ish. I'm trying not to complicate this, right? Those of you who come and go from these places know that if you use something that doesn't automatically adapt, and regrettably your cell phone chargers, your computer chargers and all now tend to make this invisible, but suppose it's, I don't know, a water heater or a hair dryer. If you bring a European water heater to North America and you plug it into 125 by putting a plug adapter on it, it's just going to get warm, because it's built to take a higher voltage. But if you do the reverse, if you take a North American appliance and you take it, like so my son did, you take a blender from here to the Philippines and plug it in, it's going to burn it out, practically speaking. But here's the thing about lighting, okay? Most of lighting circuits in a contemporary theater are wired for 125 volts in North America. Because the engineers designed the systems, they picked nice, easy numbers like 20 amps. And so a 120 volt system running at 20 amps gives you a capacity of 2,400 watts, or in the jargon 2.4K, because it's 2,400 is the same as 2.4 kilowatts, 1,000 watts. And if you ask a lighting technician, what's the capacity for lights in Studio D, they're going to say something cryptic like, well, it has 96 2.4K dimmers. So that means that we actually have a relatively simple answer or way of answering the question, how many instruments can you put on one of our circuits and dimmers? We'll get to that part of the picture in a minute. And somebody's going to say, well, how big are the lamps in them? And you're going to say, okay, they're 500 watt lamps. And that person's going to say, well, just add up 500 watt lamps until you can't fit any more on 2.4 kilowatts. And the answer, therefore, if you're being straight, is 4. So 4 500s gives you 2,000 watts, and you can put 4 of them in. Practically speaking, the systems are designed to make your operation relatively safe, but we'll get to that in a minute. All right. So please, if some of these concepts that we need to understand, such as watts, volts, and amps, don't make sense to you still, there's lots and lots of information and different ways of explaining it if you just Google, and it'll work well. Okay, how does this translate to the systems that are wired into the grid and that we need to use for all of our conventional, and actually, in fact, in many ways for our intelligent fixtures in the theater? What's on screen now is a simple diagram of one 120 volt alternating current wiring circuit, and circuit is the key word here. In order for electricity to flow, there has to be a complete pathway. This may be no-brainer for lots of you. So you've got a source of electricity, the wiring system that supplies the building with everything that's behind that. But this is a simplified version of it. You have in this drawing here a white wire representing the neutral, 2 outlets, and that 2 vertical slashes is the configuration for a 120 volt 15 amp plug. It's missing a round hole, which would be the ground. I'll talk about that in a second. It's protected by a fuse. This is old school. Nowadays, it would actually be supplied by a circuit breaker. The circuit breaker or a fuse is simply a component that is designed to switch off or fail when too much current is trying to flow in the circuit, because either something has failed, or the black wire and the white wire in most cases has been joined somehow inadvertently. And in that case, what's really happening is that all the power available to that circuit is flowing through without being limited by what the work is that it's supposed to be doing, namely running two lamps, for example. This here represents a switch, and that would actually be not a switch in any of our circuits, but a dimmer. There are 96 of these in either Studio D or Studio T. The same is true in the assembly space. There's 3 times that many in the big part of the Wong. But this is one, right? This is one 20 amp in our case circuit. So I said this was set up to be sensible and hard to go wrong with. And what I meant by that was that the largest lamp, the highest capacity lamp, or the highest wattage lamp in a typical theater light in our building is 1,000 watts. And for the most part, numbered circuits have 2 plugs. And so as long as you're just plugging into the regular plugs, you would have to work to go wrong, because you'd have to find a way of calling for more wattage than the circuit is designed to handle or the dimmer is designed to regulate. And so the way that would happen would be if you were using circuits that occasionally have 3 locations, or that you got out some kind of a connector that allows you to split the wiring, a Y connector or a twofer, we refer to them as. And then you have to think. You really have to think, because you don't have to think hard, because you're just adding up wattages, but you do have to pay attention. What will happen if you go wrong? Well, the circuit breaker in the dimmer rack will simply switch off, and you'll have to figure out why it went wrong and correct the condition, and then you can switch it on again, and everything will be fine, all things being equal. What's missing from this drawing, though, is the wiring for the ground, or sometimes it's called earth in Europe. And what that is another wire that connects anything in the system that you can contact, whether it's the pipes, the outlet boxes, the body of the lighting instrument. And if you were able to trace all those connected parts together, you would find out that they literally went to a connection that went right through to earth, right through to the ground. Reason for that, and the reason why you do not mess with that or take off the 3rd connection on plugs or bypass them unless you are quite knowledgeable, is because the alternative to the ground wire is your body, and it does not take as much electricity as you think to do serious damage to a human body. So do not mess with the grounds. If something doesn't seem to be working and you're not knowledgeable, point it out, and please do go to the trouble of reading the electrical safety document that I will put on Canvas as well. So now it's time to see how this all gets applied in practice. Let's go back to the beginning to this lighting plot. Technical person setting this up, or the designer who put it all together, is very seldom going to be working anywhere near the maximum capacity of this system, because it has 96 dimmers and circuits, each of which can handle 20 amperes worth of electricity. And although you might turn off a massive breaker somewhere in the building, if you loaded them all to capacity and turned them all on, you also would be able to bake cars in the room, because you wouldn't need anywhere near that much lighting. What this is typically about is about choices. So it's almost never the case that a heavily loaded lighting plot is going to be running at all close to full intensity and with all the circuits running. Not a chance. Maybe a small plot, yeah, but not typically. It's typically about choices. And so if you look at any one of these instruments, you're going to see that there's a pattern here. If we look at the way it's set up, let's pick this backlight here. Okay, so what you've got is choices. So this number here represents a what's called a channel. It's like an address, all right? And you can see that there's a pattern. Look, 21, 22, 23, and it goes on like that. So there's 23. Going over, it'll go, let me just take another look at this. I guess it's going in this direction, 24, 25, 26. What's being represented here is this pattern. It's not the same lighting plot, but look at this. This is an organized pattern. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, that's wrong. 6, 6. Oh no, what they've done here is compromise. So 1, 2, 3, 4, 5, but they've done 6, 6, 7, 8, 8, and so on. So it hasn't, it's only the very downstage, the very front row that is individually set up. And the same thing is true as you go through each one of these lighting plots. All right, on the lighting plot, this would be represented by information, setup. Like here's a different lighting plot. This is the student choreographic one, and this is down here the legend, which I've simply captured and moved over, and it gives us quite a bit of information. So for example, it tells us what this icon represents for an instrument, and it also tells us, gets a bit blurry if I take it out, but so this is the in front of it is the number, the color number that identifies the color filter that goes in there. And key here for us, this says channel and dimmer. And so on this lighting plot, which is the one that really is representing this pattern here, but on this lighting plot, in the hexagon is the dimmer, and in the circle is the channel. Okay, so what are those two? The dimmer in our theaters is actually not only the dimmer, but it is the dimmer and the circuit number, because most contemporary theaters are now wired so every numbered circuit with its however many plugs it has, 2, 3, or 4 plugs, in our case 2 or 3, every circuit has its own dimmer. Dimmer per circuit is what it's called, and they are simply laid out logically in the room, although it may be that logic is not so obvious to you, because if you were to go and look in this room very carefully, you would find that there were boxes on the ceiling. Here's how they're represented on the drawing, right? So here is circuits and dimmers, or circuits, plugs actually, that represent the hard electrical wiring that they are connected with. And in this case, it starts over here, 1 to 6, 7 to 12, going across, 13 to 18, 19 to 24. It's done that way because it's common practice to orient systems in a theater according to the point of view of the performer facing the audience. Now, obviously, in this theater, it's arbitrary because there is no fixed configuration, but it's just done to assume the most common configuration. So there is 7 through 12. If I remember correctly, at the opposite end of the room, sort of diagonally across the room, there is 1 to 6, 7 to 12, and so on. And in this room, I believe, which I think is this is Studio D, there are also circuits on the walls, and sometimes those are repeats of circuits overhead in the grid. But what's behind this? Why would you have 1 through 6 here and 1 through 6 diagonally across the room? Answer, because you're going for flexibility, you're going for ease of hookup, you're going for the least likely to require you to run additional cable. And the assumption, not always successful, but the assumption is that you're not likely to be using as many instruments here in a configuration like there as you are over here. And more importantly, you're extremely unlikely to be using circuit 1 away out here and circuit 1 away out here at the same time, because it can't be lost that if you plug into circuit 1 in 2 locations, the instruments connected that way are going to do exactly the same thing. They're going to turn on, they're going to go to the same percentage of their maximum intensity, they're going to turn off, they're going to act as if they were hardwired together, which in effect they are. So the circuits, and therefore the access to the dimmers, is arbitrarily and evenly spread all over the room like this. On the other hand, the person wanting to use this, the designer, and the person operating it, the lighting operator, are not going to want to deal with the fact that, for example, if they want to bring up these 2 front lights, they're going to have to go with 88 plus 87 plus 83, like that. They're going to want to go 15, through 17, just for organization and for common sense accessing the information that they need. So what this represents here is the pattern of control. And what this represents, on the other hand, these numbers in the hexagons, that's just pure convenience. What's available, the nearest available circuit that is not otherwise in use, that I can plug this instrument into, and then later when I'm setting up my control system, I can create a pattern of organization that makes it easy for me to go ahead and design, right? And so that's the concept of circuits and dimmers, which are in our theater essentially one and the same thing. Not exactly, but in practical terms, from hanging and focusing. That's done for convenience, and organization and control is established later. So up to now, we've been talking about working with conventional lighting instruments. This lighting plot here, which is the student dance show Meraki, the same one that has this pattern of control here, they were quite deliberately, the designers that is, held to, for the most part, to fixed focus conventional lighting instruments. And every one of these then of that category has to be connected somehow to a dimmer. In this plot that we looked at in the very beginning, there are some fixtures that are not that at all. So, for example, these curiously drawn ones here are actually moving lights. I don't know where, frankly, I have a feeling, oh yeah, no, here we are. So here's the legend for that. And this is a rather basic moving light called a Mac 250, quite old. Some of the instruments apparently had scrollers, color scrollers on them, whatever that is. We could talk about that. We will after a bit. But those instruments do not, in fact, actually run through a dimmer. So these are the first intelligent fixtures we're talking about. And their channel of control here is organized in the same way I've been talking about. But in this case, and for these instruments that are pointing towards the audience but really have a mirror in them that moves, called an IQ, those instruments are actually using the dimmer, which is represented by this number here, purely to power them. The dimmers have been set to just supply power, which is one of the ways you can get constant power to these instruments, not always the best. And the actual control of the lighting instrument is bypassing the dimmer and coming directly from the console. So what do I mean about that? This is the way the overview, simplified overview of a lighting system set up with both intelligent lights and conventional instruments. So what we've been talking about is dimmers powering circuits into which are plugged conventional instruments. The dimmers are controlled from the dimmer board, but, and we'll talk about this in a minute, but so are intelligent fixtures that do other things. If they dim and go up and down the same way as a conventional fixture, the capability of doing that is usually built into the instrument itself. It's not caused by it being run by a dimmer. So even if there are dimmers, they are set to on and they don't get controlled. The control board is controlling both of these through, in essence, a temporary computer network. Very much the same way as you would plug your laptop into a printer, or you would plug your, a small temporary network that would set up, say, a set of computers and printers and routers and all that stuff. You know that, although you may not have thought about it, but when you are accessing the internet, for example, you need an IP address. Well, what IP stands for is Internet Protocol. And it's simply if you like, a computer language. There are tons of them that you use. Maybe you're aware of them, maybe you're not. When you type on your keyboard, you're using a protocol called ASCII, for which every letter and capital and has a numerical code, and that's a translation. Okay, in lighting control, it's called DMX. So we talk about DMX as if it was, solid stuff like the wires. Have you run the DMX? Have you done this? Have you done that? Really, what we're saying is, have you set up the wiring, which is like as durable as, say, a microphone cable, not because it needs to be that heavy to carry, in essence, data. Could be lightweight cables like you use to a USB connector to plug two components of your computer system together. But in the theater, things are made to be durable, and they're made to have connections that won't come off. And it's all about reliability and constant connection rather than about does it need to be that big to do its job. So setting up the DMX wiring is a way of saying wire up a local area network. Some of it is permanent, so that permanently there's network wired to the dimmer room that controls from numerous locations where you can patch in a control board. Sometimes there's a permanent, sometimes it's temporary, and we're going out to various components that run the intelligent lights. And I think I'll just leave for now how that's done, because, not in the sense of how it's wired, but in the sense of what's actually happening to control intelligent lights, because it runs from the very simple to the incredibly complicated. But this gives you a sense of the control of the total system. There's things missing from here. So, for example, there's permanent power going to the racks. There's permanent wiring going out to the ceiling, lots of it. One complete circuit for each numbered circuit in the ceiling, coming from each numbered dimmer in the racks. There are permanent in-the-wall wiring setups for the computer data, and then we connect into that and run it to temporary components or routers or distribution components, and then connect the lighting instruments up to that. But the simple way of understanding this is that these blue lines are basically a data network, and this is actually a very significant change from the beginning of my career, but don't worry about that at the moment. I'll maybe talk a bit about that later. So this is the overview, and then see, so from this this plan here that Christian set up for how he wants to access and a plan of organization for him to call up various lighting instruments or groups of lighting instruments and to make it simple for him and simple for the operator. When he's drawn that all up in this, all of this information is generated in Vectorworks, and it is comparatively simple for the program. You just simply call up a paperwork sheet once you've done the initial work, and you print out something like this. If you have chosen this pattern of control here, 1, 2, 3, 4, 5, 6, 7, 8, and then that has, or these are the circuits, right? And then this is the, I'm sorry, but I don't know if this is exactly the same show because I didn't pay a whole lot of attention, but this one is organized by circuits and dimmers, so they look organized and the channels look erratic, but the reality is that the thinking is organized around the channels, and it's in fact the organization of the dimmers that turns to be less important because nobody much cares. And then when he chose a particular instrument, it had, as part of its data, it had code built in. I don't know about daisy house floods. That could be something that Christian put in, or it could be, well, now that I'm looking at these, I think these are what he is thinking about these as. So he's labeled these according to his thinking and organization. And then this is a way of keeping track of it. And so it's very, very systematic. And the most important thing to understand is that if this computer-generated lighting plot is kept up to date and organized, then you are doing the work of the mechanical organization as you go on. And that's a gigantic benefit compared to you design the lighting, and then after you've figured that all out, then you sit down for a couple of hours and generate paperwork that the crew can use. So to wrap this section up, in a normal semester, if we were in there and we were actually hanging lights, what would be happening? Well, probably you would start with a completely stripped out lighting grid. There'd be nothing hung here. You would generate a piece of paperwork, which I don't have one handy right now, but you could simply ask Vectorworks to print the piece of paperwork, which is the complete list of everything that is on the drawing. So I guess, here's a count for the color summary, which for some reason is on this. The filters, these are filters for the lighting instruments. It could equally give you a count for every single one of these lighting instrument categories. And then we would systematically go through the space on lifts, or if it was over the seating, on ladders, and hang these lighting instruments and connect them to lighting circuits. Very typically, the circuits and dimmers would not be identified on the drawing usually, because it's a waste of effort usually, because typically you just go, okay, the closest box to me is 7 through 12, and somebody using highly sophisticated technology, namely a list of numbers from 1 to 96, would say, okay, the only ones not already crossed off and therefore in use, can you plug into 11? And you go, not quite. Can I have a 1 meter cable or whatever? It's usually identified now by color code, and you would connect it, like physically connect from the cable on the lighting instrument to the cable to the plug on the box, following lots of different practical considerations like neatness, the ability to move the lighting instrument, and so on. And you would go, okay, I'm in 11, and somebody would either go on their laptop and put 11, or in this case, say 8, into the dimmer location, and it would pop up on the drawing and also be built into the records, so that when you printed that piece of paperwork, it would be there. Or they would just do it in paper, and somebody would go home after the show, or sit there after the crew went away and update everything. And then the same type of a process would be followed to hook up all of the temporary computer control, the DMX wiring. And there are various components that control DMX lighting equipment. Some of them have intermediate components that control groups of lighting instruments. Some of them just connect directly into the instrument itself. And each of these networks is usually broken down into smaller components, so that you don't have cables that run unnecessarily all over the place, but you have you could think of them as pieces of distribution equipment that take a signal and split it and send it out into a smaller group of lighting instruments. Each of the intelligent fixtures, and in fact each aspect, if you like, of the intelligent fixture has to be given an identifier, an address. And so that's rather, I won't show you particularly, but for example, on this Mac 250 here, you can see this has a dimmer number, it has a channel number, and it also has this here, which identifies its address and the fact that it's in a separate universe, and which is lighting board think, and it takes the equivalent of 15 channels to do what it does. Fortunately, most of that is now automatically done the minute you connect it into or not connect it, but the moment you enter it into the lighting board software, the software is programmed to automatically go, oh, you tell it it's a Mac 250, it goes, what's the starting channel, or really, what's the starting address? And the minute that you give it 40, it reserves 15 in the back, because it knows it needs 15 different addresses for this lighting instrument to do what it does. And some of them need 50. Okay, finally, it's important to understand that everything that has been accomplished up to this point has been ultimately driven by the lighting designer's experience of rehearsals, their desires as to what they want to be able to accomplish, and so on. But it's in fact only the beginnings of the design process. It's more or less like a sculptor got their tools and their materials together, or a painter purchased the paints they thought they would like to have for this particular work that they're going to do, and they assembled their workspace and they got it all ready to go, and now they're ready to do a painting. So in this case, it's a long, complicated, and a mechanical process that requires very significant understanding of how this could be done, or really great collaborators. But it in of itself is based on design, but it's really the beginning of the process. And now that it's all hung, focused, colored, and ready to go, now the designer can actually begin to execute their work. So you need both. But the drawing and even the hang and focus is still preparation for the actual design work itself. Okay, thank you.